Hello and welcome to Chapter 3 Digital Communication Techniques. Alright, so the objectives for this chapter is to discuss the advantage and disadvantage of digital communication system while describing the operation of digital service or device. Explain the process of modulating, formatting, transmission, and receive the digital communication. Right, the goals in communication system is to maximize the transmission rate, maximize the system utilization, the bit error, the requirement system bandwidth, minimize system complexity, and to minimize required power. Okay, this is the general diagram of what we want to do in communication system. So, for digital communication covers a broad range of communication techniques, including digital transmission and digital modulation. In digital transmission, pulses are transferred directly between two or more points in communication system, and it requires a physical connection between the sources and the destination, like a pair of metallic wires or coaxial cable or optical fiber that we see in our daily lives. Digital transmission can have analog or digital inputs, but the analog input should be converted into digital form prior to transmission. The digital modulation involves the transmission of digitally modulated analog signal between two or more points. So why do we use digital communication? It is an easy way to regenerate the distorted signal. Okay, it is easy to reduce the noise in your signals. It also regenerative repeaters along the transmission path and detects a digital signal and retransmit a new clean noise-free signal. Okay, like we've mentioned just now. So with these repeaters, prevent accumulation of noise along the path by using a feedback system. This is not that possible with analog communication like AM or FM, and the input to digital system is in the form of a sequence of bits. So this is how you would see a pulse degradation or and regeneration. Okay, so with this is an original pulse signal. Okay, and there are some signal distortion as well as degraded signal, and signal is badly degraded, and the application to regenerate the pulse. It is a way to change the signal where it is distorted by noise, but with digital signal with digital communication we can change back all of that into the original signal in a simpler way. So why do we still use digital communication, and why is it better than analog in our daily use? The hardware is more flexible, but it is implemented with permits and use of microprocessor, mini processor, and digital switching. Okay, the shorter design and production cycle, it has low cost, and the use of LSI and VLSI in the design of component and system has resulted in lower costs. With digital communication, we have easier and more efficient to multiplex several digital signal, and it is easier to use digital multiplexing technique. We will see later down the road. So there are with digital signal we can combine many different types of signal, where AM we can only send like sound signal or a video signal. Same goes for FM. But with digital communication, we can send all of these type of data, like data, voice, text, etc., in the same frequency or in a synchronous way. Okay. By using digital techniques, it is possible to combine both formats for transmission through common medium, and the encryption and privacy techniques are easier to implement. Digital communication has better performance, and it is inherently more efficient than analog in realizing the exchange of signal to noise ratio for the bandwidth. And with digital signals can be coded to yield extremely low rates and high fidelity as well as privacy. But with all of these advantage and the reason we use digital communication, there is a few advantages. Okay, it requires reliable synchronization, and it requires analog to digital conversion in high rate if we use an analog input. It also requires a larger bandwidth to transfer all of that multiplex data, and the probability to error or bit error rate is quite high. So there are three primary reasons for growth of digital communication. It is to increase the computer usage, which we are used a lot in our daily lives, the benefits of digital transmission methods, the conversion of telephone system for analog to digital. Okay, computers and digital communication, we will use them for file transfers, electronic mails, computer peripheral ring, internets, and local area networks. All of this is used by using digital communication. So these are the key things that we need to learn for digital communication, which is formatting, modulation, demodulation, and detection. For formatting or source coding, we transform the source information into bits digital symbol by digitizing or assuring the compatibility between the information and the signal processing within the DCS. It is a way to select compatible waveforms and introduce redundancy, which facilitates accurate decoding despite the errors. And it is also essential for reliable communication. Same goes for AM and FM. Modulation is required in digital communication also. It is the process of modifying the signal to facilitate the transmission. So we want to change the input signal into a certain signal so that it can be transferred by the transmitter and well received by the receiver. Demodulation reverses the process of modulation, still the same as previous topics, and it involves the detection and retrieval of the info signal. So how the data conversion in digital communication? So data conversion is important so that it can convert data from analog form into digital form. As you can see from the diagram, analog form is in random punya signal, while in digital it changes all of that data read by the modulator to a digital signal by using binary numbers. Okay, by having that change, we must use analog to digital conversion. And with this conversion is a process of sampling or measuring the analog signal at regular times intervals. And at the time indicates by vertical dash line, instantaneous value of the analog signal is measured and proportional binary number is generated to represent that sample. So as a result, the continuous analog signal is translated to a series of discrete binary numbers representing samples. So as you can see, this is uh, the digital signal by sampling from the analog signal by looking at the amplitudes from each point in different time. Okay, by sampling process, it is a process where we sample the reciprocal of the sampling interval t, but like I mentioned just now, in different time. Okay, the sufficient number of samples to retain the high frequency information in the analog signal. Minimum sampling frequency is twice the higher analog frequency contents of the signal by using Nyquist frequency. So your Fn should be more than your Fm by double, okay? And Fm is the frequency of the input signal. Same goes for AM and FM. We still have frequency, a modulated frequency. For the bandwidth, it is still limited signal by Fn equal to 2 times with f2 minus f1. So DA conversion is just a reversal of AD conversion. It's to translate the multiple binary numbers back into the analog voltage. And because of the input in binary numbers represent specific voltage level, the output of the DA converter has a stair-step characteristic. Since the steps are very large, the resulting voltage is only an approximation to the actual analog signal. So the signal we receive from the transmitter to the receiver, it would be a little bit, there would be a little difference compared to the original signal because it is only a prediction or approximation from the original signal that has been changed into digital. However, the stair step can be filtered out by phasing the digital analog converter output through a low pass filter with an appropriate cutoff frequency. So a frequency calculation is easy enough. It is just 1 over t, where t is the time it takes to change the digital signal. Alright, and the nth harmonic, it is where the Fn depends on the number of harmonic equals to, like I mentioned, the number of harmonics times with F signal frequency. So Nyquist frequency Fm is the minimum sampling frequency, and it should be twice the highest analog frequency content content of the signal. Okay. Alright, for minimum sampling rate, the equation should be equals to 2 times f of the nth harmonics. Okay, as you can see from this example, an information signal transmitted digitally is a rectangular wave with a period of 53.4 microsecond. This is your time. Okay, it has been determined that the wave will be adequately passed if the bandwidth includes 7th harmonic. Calculate the signal frequency, right? So the signal frequency over here is f equal to 1 over time, and time has been given equals to 53.4 microsecond. So you should use this equation, just substitute 53.4 microseconds into here, you will get the frequency. Alright, the fifth harmonics, okay, it asks us about the fifth harmonic. So your fifth harmonic, you just use this equation where it is equal to n times f, the f we have searched for now. So it is the fifth harmonic, your n should be 5. So 5 times with this value that you have calculated. The minimum sampling frequency, Nyquist rate, is this. So you just times the value you have found for the nth harmonics with 2, and you will get your minimum sampling rate. So a harmonic of a wave is component frequency of the signal that is an integer multiple of the fundamental frequency. For example, if the fundamental frequency is f, the harmonics have frequencies of 2f, 3f, 4f, and etc. The harmonics have the property that they all are periodic at the fundamental frequency. Therefore, the sum of the harmonics is also periodic at the frequency, and the harmonic frequency are equally spaced by the width of the fundamental frequency and can be found by the repeatedly adding that frequency. So for example, if the fundamental frequency first harmonic is 25 Hz, the frequency of the next harmonics are 50 Hz, 75 Hz, and 100 Hz. All of them are added to each other. Alright, what are Nyquist rate? So Nyquist rate is a continuous function. Xt is sample at a constant rate, Fs. There is always an unlimited number of other continuous functions that fits the same set of example, but only one of them is bandlimited to 1 over 2 Fs. So Fs here refers to your frequency in sample, which means that its Fourier transform Xf is 0 for all justified f more than 1 over 2 frequency sampling. So it follows that the original function xt is bandlimited to 1 over 2 fs, which is called the Nyquist criterion. There is one unique function that interpolation algorithms are approximating. And in terms of function on bandwidth, as depicted above, the Nyquist criterion is often stated as fs more than 2b. Okay? And 2b is called the Nyquist rate for function with bandwidth b. When the Nyquist criterion is not met, where b is more than 1 over 2 of fs, a condition called aliasing occurs, which results in some inevitable differences between xt and the construction function that has less bandwidth. And in most cases, the differences are viewed as distortion.